Hello students, welcome back to my YouTube channel. Today we are discussing another PYQ from JEE Advanced. To be specific, this is a question from the 2019 paper 1 of JEE Advanced. This is also from the topic of electrostatics. Let's read the question. A thin spherical insulating shell of radius r carries a uniformly distributed charge such that the potential on its surface is V naught. A hole with a small area alpha into 4 pi r square, where alpha is very small compared to 1, is made on the shell without affecting the rest of the shell. Which of the following statements is correct? Option A. The potential at the center of the shell is reduced by twice alpha V naught. Option B. The magnitude of electric field at the center of the shell is reduced by alpha V naught by 2r. Option C. The ratio of the potential at the center of the shell to that of the point at half r from the center towards the hole will be 1 minus alpha divided by 1 minus 2 alpha. Fourth, or D option, the magnitude of electric field at a point located on the line passing through the hole and the shell center on a distance 2r from the center of the spherical shell will be reduced by alpha V naught by 2r. So this is the question. You can pause and read it again if you wish. Let's get into the first part, which is what are the key ideas used in this question. The first key idea that is used in this question is the principle of superposition, which states that if you want the net potential or electric field at any point, you simply have to add the potentials and electric field due to all the elemental charges in space at that point. So, suppose you have 4 elemental charges Q1, Q2, Q3 and Q4. The net electric field at any point P will be the sum of the electric field due to the individual charges Q1, Q2, Q3 and Q4 at that point. For potential, you need to only take the algebraic sum because the potential is a scalar quantity. Whereas for the electric field, you need to take the vector sum because electric field is a vector quantity. This is the first idea that we are going to use. Mostly students are very comfortable with this idea. Then, this is the very important idea in this particular question. We are going to make use of the shell theorems. What does the shell theorem state? There are two shell theorems. The first shell theorem states that for any uniformly charged spherical shell, the net field at an interior point will be 0. Means doesn't matter which point you select at interior of the shell. At all those points, the net electric field is going to be 0, and the net electric potential at any interior point will be equal to the potential on the surface of the shell. So potential on the surface of the shell is kq by r, which in the question is given as V naught. So at any interior point, the potential will be equal to V naught, which is kq by r. The second shell theorem states that for a thin uniformly charged spherical shell, the calculation of field and potential at exterior point. Now this is very important. In theorem 1 we discussed about the calculation of potential and field at interior point. But in theorem 2 we are discussing about the calculation of field and potential at exterior point. So for all exterior points, you can treat the charged shell as a point charge placed at its geometric center. I hope this is clear. So for all exterior point, we will be treating the uniformly charged shell like a point charge placed at its geometric center. The third important idea that we need to know is that the patch that has been removed, that can be treated as a point charge. The question is why it can be treated as point charge? Because you can see alpha is very small compared to 1. That means the surface area of that patch is very small compared to the surface area of that entire sphere. Therefore, we can treat the patch like a point charge. Now let's dive into the solution. The first option asks us to calculate the reduction in potential at point C, which is the center of the sphere. So what we're going to do is, we're going to use shell theorem number 1. What does shell theorem number 1 state? It states that the potential at the center of the sphere must be equal to potential at the surface, because the center of the sphere is an interior point, right? This is an interior point. So that means potential due to the remaining sphere plus potential due to patch should add up to give you V naught at the center. The potential due to the patch is easy to calculate because patch is a point charge. So for the calculation of the potential of patch, we can simply write KQ patch divided by R. And we can use the formula that charge on the patch will be equal to surface charge density into area of the patch. So if we use this particular formula, you will see that dA is already given in the question as alpha into 4 pi r square. So alpha into 4 pi r square multiplied by sigma. But wait, sigma into 4 pi r square is the total charge on the sphere. That means sigma into 4 pi r square will be replaced by Q. So it's V naught minus alpha KQ by R. But again, alpha KQ by R itself is V naught. So the potential due to the remaining portion of the sphere at the center of the sphere will be V naught into 1 minus alpha. So the reduction is potential. The reduction in potential is minus alpha V naught. It has reduced by an amount alpha V naught, which tells that option A is incorrect because option says that there it is 2 alpha V naught. That is what option A says. If we have a look, option A says that the reduction in potential at center of shell is 2 alpha V naught, which is wrong. By superposition, we see that the reduction in potential is just alpha V naught. Now, if we consider the interior point electric field, it should always be 0. Again, we use the same idea. Electric field due to the remaining portion plus electric field due to the patch should be equal to 0. That means electric field due to the remaining portion plus k dq by r square into r cap should be 0. So I am assuming that this charge is positive because in the question they have not mentioned whether the charge is positive or negative on the spherical shell. So by default we will assume it's positive. So electric field due to the remaining portion can be calculated by sending this term to the RHS and substituting dq as alpha into sigma into 4 pi r square. Again, sigma into 4 pi r square can be substituted as total charge Q. So this shows that electric field due to the remaining portion is minus kq by r square into alpha, and I will substitute kq by r as V naught. One of the r's will remain in the denominator itself and you will get minus alpha V naught by r, which indicates option B is also incorrect because they said that it will reduce by alpha V naught by 2r. Moving on to checking the potential at the interior point again, but this time it's not the center. This time they are asking it at this point P, which is at a distance r by 2 from the center of the sphere and r by 2 from the patch as well. Again, potential is a scalar. So potential at any interior point must be equal to kq by r. We have used that idea. Other than that, potential of the patch I have calculated by assuming a point charge of alpha q. So k into alpha q divided by distance of that point from the point charge is r by 2. This will tell you that the potential due to the patch is going to be 2 alpha V naught, and we can send that to the LHS. So the remaining portion's potential at point P will be equal to V naught minus 2 alpha V naught, which will be V naught into 1 minus 2 alpha. Now what are they asking in option C? They are asking us to find the ratio of the potential at point C due to the remaining sphere and potential at point P due to the remaining sphere, where of course C is the center, which we have already calculated. Potential at C is V naught into 1 minus alpha, and potential at P just now we have calculated V naught into 1 minus 2 alpha. So if we divide the two, we get 1 minus alpha by 1 minus 2 alpha, which tells us that option C is correct. Finally, moving on to the reduction in electric field at an exterior point, which is at a distance 2r from the center. What we can do is, we can calculate the electric field at exterior point by replacing the entire charge of the spherical shell by a point charge placed at its center. So electric field due to remaining portion plus electric field due to patch must add up to give you kq by r square, where of course we are going to substitute this small r as 2r. So again E remaining plus I have treated the patch as a point charge of charge alpha q and I have substituted small r as 2r. So once we do that, electric field due to the remaining portion after calculation is seen to be reduced by alpha kq by r square. This can simply be written as alpha v naught by r, because I can write kq by r as v naught. This shows that option D is wrong, because option D claims that the reduction in electric field is alpha v naught by 2r. So in conclusion, only option C is correct. So we have learnt three important ideas that are used to calculate the potential and field inside and outside a spherical shell. So please remember to carefully go through the shell theorems. Now let us see a question which is a modified version of this question, which might appear in future in JEE Advanced. So dear students, this is a modified question from the previous JEE Advanced question that we just solved from 2019 paper 1. Have a look at this question, I'll read it out for you. It says, a thin spherical insulating shell of radius r carries a uniform distributed charge of plus q. A second uncharged metallic conducting shell of radius 2r is placed concentrically surrounding the first shell. A small hole of area dA is equal to alpha into 4 pi capital R square, where alpha is very small compared to 1, is made on the inner insulating shell, effectively removing the charge from that area. Which of the following statement is correct regarding the electric potential on the outer conducting shell? Is the potential same as option 1? Option 2, the potential decreases by kq alpha by 2r. Option 3, the potential decreases by kq alpha by r. And option D, the potential increases by kq alpha by 2r. So try this question out and kindly give your answers in the comment section. I'm very eager to hear them. Thank you very much for watching this video. Please like the video on your way out and subscribe to the channel. Thank you.